So we've looked at capacitors in series and capacitors in parallel, and now we can combine the two and say, let's look at circuits that have combinations of those. And so this really one of the simplest versions of that I can give you is a battery connected to three capacitors, sorry, right? And ask you what is the total capacitance of this circuit, right? And then we have to kind of break it down and say, well, this section of the circuit is a parallel section. That is to say, the two bottom sides of these two capacitors are connected by a wire, and the two top sides are connected by a wire. That says that these two guys are in parallel. This circuit can go this way, or a circuit can go that way. And so we can say, look, from the previous section, we can call this red box CP, the total capacitance of that, and then we just use our parallel rule there, and we can say CP equals C1 plus C2. Right? Or sorry, C2 plus C3. Right? CP contains these two guys, and it's C2 plus C3. And then we can look and say, well, so we can reimagine this circuit then this way, and we can say, well, it's got C1 here, and now we just got CP here. Well, now I have just one path through my circuit, and so these two guys are in series now, and I can say, look, if I want to treat this as a single capacitor, I can say, well, we'll call it C series, right? And C series, a series capacitance just gives me 1 over C series is equal to 1 over C1, in this case plus 1 over CP. Right, and so now this becomes the total capacitance of the circuit. If I wanted to write it all the way out, I would say 1 over C series is equal to 1 over C1 plus, so I know that C parallel is C2 plus C3, so I can say 1 over C2 plus C3, right? And that would be 1 over C series. And so I can calculate the series capacitance this way. And so if I do a numerical example of this, if I pick some convenient numbers, I can say, well, let's pick C1 equals 20 microfarads, C2 equals let's say 10 microfarads, and C3 equals 30 microfarads. And so then we can say, well, look, C parallel is just C2 plus C3. That's equal to 10 microfarads plus 30 microfarads, which is 40 microfarads. So the combinations of these two guys gives me a parallel capacitance of 40 microfarads. And so now I have a 20 microfarad capacitor, that's what this guy is, in series with a 40 microfarad capacitor. Maybe I'll write that in red. And so I can say, look, the total capacitance, 1 over C series, is equal to 1 over 20 microfarads. Nope. Plus 1 over 40 microfarads. And so if I just want to avoid the calculator, I can say, well, that's 2 over 40 microfarads plus 1 over 40. I just found a common denominator, right? Or 3 over 40 microfarads. So C series is 1 over that, which is 40 microfarads, divided by 3, which is 13.3 microfarads, and that's the total capacitance of my circuit. So let's do another example. In this example, I have this circuit. It's a little different than the last one. It's got two branches that are parallel. One contains a single capacitor, the other contains two capacitors in series. The capacitors are C1 is 10 microfarads, C2 is 20, and C3 is 60. And the voltage here is 12 volts. And you know, we can just answer a bunch of questions. The first one maybe is what is the total capacitance of the circuit, right? And so now we have to kind of think our way through this a little bit and say, well, these two guys are in parallel, but I can't do a parallel calculation yet because I've got two on this side that are in series. And so I have to start with the series, and I can say, well, 1 over C series is equal to 1 over C1 plus 1 over one over C2, keep doing that, plus 1 over C3. And so that says 1 over C series is equal to 1 over 30 microfarads plus 1 over 60 microfarads. Well, 1 over 30 microfarads is the same thing as 2 over 60, so for the common denominator, if I add those together, I get 3 over 60, and so C series, 1 over C series is equal to 3 over 60 microfarads, which is 1 over 20 microfarads. And so C series is equal to 20 microfarads. I'm not done yet because now these two are in parallel, and so I can say if my total circuit looks like this, right, then this guy I'm going to call C parallel, and it's the combination of C1 and C series in parallel, and so C parallel is equal to C1 plus C2, because C1 plus C series, because that's our parallel formula, and so it's equal to 10 microfarads plus 20 microfarads is equal to 30 microfarads. So that's the answer. The total capacitance of my circuit is 30 microfarads. And now I could say, what's the charge? I can maybe ask another question and say, what's the charge on capacitor C1? Well, if we go back to our formula, Q1 is equal to C1 V1, right? That is to say the charge on a capacitor is the capacitance times the voltage. Well, we already know what these numbers are, right? The capacitance is 10 microfarads. Notice that this battery, either end of the battery is connected to either end of the capacitor. Doesn't matter what else is going on. If the battery is connected to both ends of the capacitor, then that's the voltage on the capacitor. And so this is just V1 times 12 volts. Sorry, 10 microfarads times 12 volts, which is 120, 120 microfarad volts, right? And so micro is times 10 to the minus 6, but a farad is equal to a coulomb squared per joule, and a volt is a joule per coulomb. And so this comes out to 120 times 10 to the minus 6 coulombs. 10 to the minus 6 coulombs, or Q1 is equal to 1.2 times 10 to the minus 4 coulombs. So that's the charge on this guy. So now we can say what are the charges on the other two, right? So this is a little trickier because I can't necessarily, so I could say Q2 is equal to C2 V2. The problem with that, of course, is that I don't know what the voltage is across this capacitor, because all I know is that the 12 volts is across the whole thing, not across just one capacitor in this string. And so I could also say that that Q3 is equal to C3 V3. But of course, I don't know V3 either. V3 is the voltage across this capacitor. What I do know is that C series is equal to, Q series is equal to C series times V series, right? And this V series is the voltage across the whole thing. And that I do know. That's the 12 volts. The 12 volts is across the whole thing. And so I can say, look, V series is equal to 12 volts. I also know C series, because we calculated it earlier, it's the series capacitance of these two guys. It's 20 microfarads. And so I know Q series. Q for the series circuit is just, Q series is 20 microfarads times 12 volts, which is 240 times 10 to the minus 6 coulombs. I won't go through that again. Or 2.4 times 10 to the minus 4 coulombs. And you say, well, what charge is that? Well, we've talked about this before. What a capacitor does, what a voltage source does, is it pumps charge from one side. For the case of these two guys, it's pulling charges off this plate and sticking them on the top plate. Okay, and so every charge that's pulled off of one of these plates is put onto one of these plates. And so these two plates carry the exact same charge. So if there's Q series in the whole thing, if there's Q series on the top of this plate, that means there's minus Q series here. And if there's minus Q series here, there's plus Q series on this top plate and minus Q series on this plate. So each of these plates, if I calculate the series capacitance for these two guys, each one has the same charge as the series capacitance. So I can say Q2 equals Q3 equals Q series equals 2.4 times 10 to the minus 4 coulombs. So if you have a bunch of capacitors in series, they all carry the same charge. All right. So now we can ask another question about this problem. We can say, what's the voltage across each capacitor? Well, the voltage across C1, we already said, is just the same 12 volts. And if we wanted to, we could check it, right? From Q1 is equal to C1 V1. We get V1 is equal to Q1 over C1. Now, we already calculated this the other way, but we can just check it anyway, right? For this guy, we got 1.2 times 10 to the minus 4 coulombs divided by 10 microfarads. And so that's equal to 1.2 times 10 to the minus 4 coulombs divided by 10 times 10 to the minus 6. A farad is a coulomb squared per joule. That comes out to 12 joules per coulomb, which is 12 volts, which is exactly what we said it was going to be. Right? It gets more interesting when we evaluate V2 and V3. So let me erase those guys and say, look, V2 is equal to Q2 over C2. Right? And so this we hadn't evaluated already. We did get the charge. The charge was 2.4 times 10 to the minus 4 coulombs divided by 30 times 10 to the minus 6 farads. And so this comes out to 8. So it's, should I do just a little math here? 2.4 times 10 to the minus 4 coulombs over. So 30 times 10 to the minus 6 is 0.3 times 10 to the minus 4 coulombs squared per joule. And if I evaluate that, I get V2 is equal to 8 joules per coulomb, which is 8 volts. And so this guy has 8 volts across him, right? And now let's see what this guy has. So V3 is equal to Q3 over C3, which is still 2.4 times 10 to the minus 4 coulombs divided by, now I've got twice the capacitance, 60 times 10 to the minus 6 farads. And so if that's just half as big as this one, that one's going to come out to 4 volts. Notice that when I add the voltage across this guy to this guy, I get the voltage across the whole thing, and I get, in fact, 4 plus 8 is 12 volts, which I already knew was the total voltage across. So if I wanted to, I could have said, well, I got 8 volts on this guy, it must be 4 on this guy. I didn't have to do this calculation. But it's nice to do this one, because then it's kind of a double check that these two add up to the 12 that I said I should have had. And so now we calculated the total capacitance for all the capacitors, the charge on each capacitor given the initial voltage, and the voltage across each individual capacitor. So now we can ask the question, well, a 40 microfarad capacitor is charged to 20 volts. How much energy is stored? Well, our formula is the potential energy is 1/2 QV. I don't have the Q here. I just got the capacitance and the voltage, but I can run back and grab my handy dandy formula, Q equals CV, and I can just stick this in here where I had the Q, and this gives me 1/2 CV times V, or 1/2 CV squared. And so I get the potential energy stored is equal to 1/2 times 40 microfarads times 20 volts squared. Right, I should probably do all my units here. So this is 1/2 times 40 is 20. 20 squared is 400 times 20. Is that 8,000? Those are my numbers. I have a times 10 to the minus 6, and then farads is coulomb squared per joule, and volt squared is joule per coulomb squared. And so this 8,000 times 10 to the minus 6 is 8 times 10 to the minus 3, and coulomb squared per joule times the joule squared per coulomb squared is just joules. And so that's my... Of course, I could have just calculated Q ahead of time, right? I could have said the charge is equal to C times the voltage, which is 40 microfarads times 20 volts, which is 8 times 10 to the minus 4 coulombs. And then if I multiplied that by 20 and divided it by 2, I would get 8 times 10 to the minus 3 joules. So I believe that looks okay.